Student, after the last class, we just discussed the complementary function to find the complementary function of a linear differential equation. Now we start to find the particular integral of a linear differential equation. The question is that what is the PI? We have already mentioned in the last lecture what is PI. PI is, we can find PI for a linear differential equation f dy equals to q is given by 1 by f dq, where q is some function of x only. If we consider the x is the independent variable, thus the PI is 1 by f dq. We have already know that d stand for ddx. If d stand for ddx, then what represent 1 by d? 1 by d should be integration dx, because 1 by d is the reciprocal operator of the operator d. Since d stand for ddx, that means it's a differentiation, then 1 by d stand for integration dx. So if we find 1 by f dq, where q is some function of x, in that case how can I find the integration of some function qx where the integration is 1 by f d? We haven't any idea what should be the integration. So when we find the particular integral, that means you just find some integration value. So there are some few cases you can find the particular integral. The first case we have already seen in your slide is that if q is some function, q is e to the power ax. Here it is mentioned that q is e to the power ax. If the right hand side is e to the power ax, then we can find 1 by f d e to the power ax. Just replace d by a, nothing more. Just replace d by a, and when we replace d by a, we got the integration value. We haven't integrate anything, just we put the value of d, just to replace the value of d by a, because here the power of e is ax. If the power of e is 2x, then d is replaced by 2, nothing more. So you can apply this rule only when if fa not equals to 0. If fa not equals to 0, because if fa equals to 0, it's represent e to the power x by 0, which is undefined, so we cannot find the pi. In that case, if it is happen that fa is equals to 0, the next case is if fa equals to 0, then we find the pi 1 by fd e to the power x, just x out from the operator, differentiate fd with respect to d once. We just find f dash d and replace d by a, we find the pi. Next one, if it is happen that if dash a is also 0, what happen? You just find pi, again we exit x from the operator, we just write x square. Here we write x square. X square 1 by f double dash d. Just we differentiate with respect to d 2 times and replace d by a. And that is the procedure to find the particular integral if the right hand side is e to the power ax. Okay. Next, the next rule for finding pi, if it is happen that the q is not e to the power x, then q is be a function of trigonometric function, say sin ax or sin ax plus b or cos ax plus b. Okay. So the particular integral, when we find the right hand side, that means the q function is sin ax or cos ax, just we replace d square by minus a square, d square by minus a square, just we replace d square by minus a square. If it is happen that d square by if d square replaced by minus a square, the result is 0, Then what to do? Just again we exceed x from the operator, just take a differentiation of f d, we got f dash d. Next we put d square by minus a square. If it is happen that d square, if we replace d square by minus a square, it may be happen that the result is also 0. That means f dash minus a square equals to 0. If f dash minus a square is also 0, here we use the norms. If f dash minus a square equals to 0, in that case we just exceed again, we just out from our integration is x, so its result become x square, and just differentiate f d 2 times, you just find f double dash d, replace d square by minus a square, we find the particular integral. So these two cases, so we just discuss these two cases. How can I find the particular integral? These two cases by some particular example. So here is the example. Here is the particular example. The first rule. When we find the first rule, just here we give an example. How can I solve a differential equation d square minus of 1y e to the power x? This one is the perfect example, d square minus of 1y e to the power x. In the last class we just find how can I find the auxiliary equation d square replaced by minus m square, right hand side becomes 0, it's become m square minus 1 equals to 0. So m becomes plus minus 1. So in the last class, according to the last class, you can easily write the complementary function. Here we mention the complementary function is yc is a e to the power x plus b e to the power minus x. A e to the power x plus b e to the power minus x, because the root are plus 1 and minus 1. Clear? So next we find the pi. We have already mentioned pi is equals to 1 by fd. Here fd is d square minus of 1. So pi becomes 1 by d square minus of 1 e to the power 2x. Here a is 2, so we just replace d by 2, it's become 2 square minus of 1. Since 2 square minus of 1, that is 3, which is not equals to 0, so you can easily replace d by a, and the result becomes e to the power 3x. That means if we integrate e to the power 2x with some another integration, we haven't any idea what should be the integration, 1 by d square minus of 1, but still we find the result e to the power 2x by 3. So the complete solution can be written as CF plus of pi. So the total solution, we just write y equals to a e to the power x plus b e to the power minus x plus e to the power 3x by 3, which is the pi. Next we consider the another example. It may be happen that the result becomes 0. So it's your second example. And the second example is just to solve this differential equation d square minus 3d plus 2y equals to e to the power 2x. Here we can easily find the auxiliary equation m square. That should be minus. Here we just mistake type m square minus 3m. That should be m square minus 3m plus 2 equals to 0. If we factorize this equation, you just got m minus 1 into m minus 2. The value of m is 1, 2. So the complementary function becomes a e to the power x plus b e to the power 2x. Okay. The second one. When we find the particular integral, it's 1 by fd, and the right hand side is e to the power 2x. So here we write the right hand side e to the power 2x. If we replace d by 2, the result becomes 2 square, that is 4 minus 3 into 2 minus 6 plus 2, that is 0. So you cannot put the value, you cannot replace the value of d by 2, because here fa is 0. Since fa is 0, so the norm says just we differentiate fd with respect to d one times. So when we differentiate d square minus 3d plus 2 one times, d square differentiation is 2d, minus 3d differentiation is minus 3, 2's differentiation is 0. So here we write the differentiation of fd, that is f dash d, which is 2d minus 3, and just we get a x out from the operator. Next, here we put d by a. Here a is 2, so if we put d by a, the result becomes 4, 2 into 2, 4 minus of 3, that is 1, which is not equals to 0. Then you can easily put the value or you can replace the value d by 2, so the result becomes x e to the power 2x. Okay, so the total solution becomes y equals to yc, that is the complementary function, plus yp, that is the particular integral. The complementary function is a to the power x plus b to the power 2x, and the particular integral is x into e to the power 2x, where a and b are two arbitrary constant. Clear? These two, the first two rules are discussed in this class to find the pi. The next rule we just discuss if the right hand side function q is sin ax plus b, or sin ax, or cos ax plus b, or cos ax. In that case, you just replace d square by minus a square. Okay, so here we give an example, d square plus 1 y equals to sine 2x. When we find its CF, it becomes c1 cos 2x plus c2 sine 2x. When we find its pi, that is our goal for this lesson. When we find pi, 1 by d square plus of 1 sine 2x, we have already mentioned that norm says just we replace d square by minus a square. That means here d square should replace by minus 2 square. It's not minus 2 that whole square, it's minus a square. Okay, so here we replace minus 2 square. So the result becomes minus 4 plus 1. So ultimate result becomes minus 1/3 sine 2x. So if you write the complete solution, first you find the complementary function. You can easily find the complementary function becomes a cos 2x plus b sine 2x, and the particular integral is minus 1/3 sine 2x. So the complete solution becomes a cos 2x plus b sine 2x minus 1/3 sine 2x. Next case, we have already discussed, if it is happen that d square replaced by minus a square, it becomes 0. What should be the next case? This one is the perfect example. You can understand d square plus 9y cos 3x. Here we not mention the complementary function, that is your homework. You can easily find the complementary function becomes a cos 3x plus b sine 3x. That's your homework. Just we find the particular integral. Okay, so particular integral, when you find the particular integral, you just write 1 by fd, and the right hand side is cos 3x. So here 1 by d square plus 9, that is fd, d square plus 9 is your fd, and the right hand side is cos 3x. If we put d square by minus a square, it's become minus 3 square plus 9, that is minus 9 plus 9, that is 0. So we cannot put d square. Okay, d square by minus 3 square. So the norm says just we write here x and differentiate the denominator d square plus 9 with respect to d one time. So the result d square differentiation is 2d, 9 differentiation is 0. So here we write 1 by 2d cos 3x. What represent 1 by d? We have already mentioned this represent nothing but integration. So 1 by d cos 3x, it is your integration cos 3x dx. Integration of cos 3x is sin 3x by 6. Okay, so the ultimate result, if you find the complementary function with the particular integral, the complementary function should be a cos 3x plus b sin 3x, and the particular integral becomes x sin 3x by 6. Sum the complementary function with the particular integral, we get the general solution. So it's the third lecture for continuation of your topic. Next lecture we should continue the other rule to find the differential. linear differential.